Good afternoon, my name is Chong Yao, and today I'll be presenting on my Capstone project, Enhancing Anomaly Detection with Machine Learning, a proactive approach using Splunk SIEM. Over the next 20 minutes, I will walk you through the problem, my approach, the results, and my recommendations. This project addresses the rising cyber threat landscape, particularly the challenges of detecting advanced AI-driven attacks. I use Splunk SIEM enhanced with machine learning to detect anomalies in security data. I applied several unsupervised models, density function, k-means, IQR, and isolation forest, and tested them against a labeled dataset. The key finding is that isolation forest provided the most accurate malicious detection, but combining models with analyst feedback will deliver the best results overall. Cybersecurity in 2025 is dominated by AI-driven threats. 72% of organizations report an increase in attack risk in the past year, and global cybercrime costs are projected to hit US 10.5 trillion. Generative AI has amplified social engineering and phishing, with 80% of phishing emails now using AI elements. The number of disclosed vulnerabilities also continues to rise sharply. Traditional tools like EDR and NDR rely heavily on known signatures. They struggle with zero-day attacks, insider threats, and subtle behavioral anomalies. Security teams are also overwhelmed by alert fatigue and fragmented visibility. This is where Splunk SIEM with ML comes in, aggregating diverse data and using dynamic baselines to detect unseen anomalies. Despite layered security, organizations remain vulnerable. That's because threats are evolving. Traditional tools miss cross-domain anomalies, and analysts face too many alerts. We need real-time, adaptive detection that surfaces hidden anomalies, correlates activities across systems, and reduces false positives. My objectives were threefold. First, demonstrating how Splunk's MLTK can detect anomalies in SIEM's workflows. Second, simulate breach scenarios such as insider threats and ransomware to validate detection. And third, provide configuration and tuning guidance for analyst-friendly, actionable results. I use Splunk SIEM as the central detection platform, applying different ML models to build dynamic baselines. Testing was done under both clean and noisy data conditions to reflect real-world challenges. The models I tested were density function, k-means, IQR, and isolation forest via Google Colab. My setup was straightforward, no VMs. I downloaded a labeled dataset from Kaggle, imported it into Splunk on my local laptop, and applied the ML models. This approach allowed me to compare results directly against known ground truth labels. Here is a view of the dataset I used. It has labels like sus to denote suspicious logs and evil to specify malicious logs. The Splunk MRTK provided density function, k-means, and IQR detection. Isolation forest wasn't built in, so I used Google Colab to run it externally. Using multiple models helped me compare strengths and weaknesses. Let's start with the smart outlier detection model using density function in Splunk MLTK. I focus on the return value field and split the analysis by event name to provide more context. The outlier tolerance was set to 0.0001, and distribution mode was left as auto. This configuration is designed to detect rare numeric deviations even if they are subtle. Here are the results. For suspicious events, precision was around 37%, and for malicious events, around 22%. However, recall was extremely low, less than 0.02%, meaning that this method missed the vast majority of true anomalies. False positives were low in number, but given the size of the benign dataset, each one still requires analyst attention. In summary, density function works for finding extreme anomalies, but it will miss low and slow or stealthy threats. It's best suited for early threat hunting, not as a standalone detection method. Next is k-means clustering. I analyzed the same return value field and set the number of clusters to 4. This was based on testing that balanced granularity with interpretability. The goal here was to see whether naturally occurring clusters would reveal distinct attack patterns. The results showed 4 clusters. Cluster 0 contained over 144,000 events, almost all malicious. This is a strong numeric signature for attack activity. Cluster 1, although small, showed a high proportion of suspicious and malicious activity, pointing to rare but high-risk conditions. Cluster 2 had extreme numeric values but was mostly benign, showing that not all outliers are threats. Cluster 3 was mixed benign and suspicious activity. The key takeaway is that clustering can reveal strong attack patterns, but analyst validation is essential to avoid chasing false leads. Now we look at the interquartile range, or IQR method. Again, I focus on the return value field and split the analysis by event name. The threshold was set to 1.5 times the IQR, which is a common starting point for statistical outlier detection. The idea here is that each event type gets its own baseline, making detection more context-aware. This method flagged 1,299 outliers across multiple event types. Most were found in common system calls like connect and open-air. Splitting by event type avoided one event type dominating the baseline for another, which improved accuracy. However, many of the flagged events were legitimate but rare, so analyst review is required to separate harmless anomalies from actual threats. Threshold tuning is critical here. Too low and you will get too many false positives, too high and you will miss real attacks. Finally, isolation forest. This algorithm isn't included in Splunk MLTK by default, so I ran it externally on Google Colab. I set the contamination rate to 0.001 to reflect the dataset imbalance and included all relevant numeric features. Random state was fixed at 42 for reproducibility. The advantage here is that isolation forest is well suited for large, noisy dataset. These are the results from the confusion matrix and classification report. The model achieved 84% recall for malicious events, meaning that it detected nearly all the true attacks. Precision was also strong, at 84% for malicious events, indicating that most flagged anomalies were real threats. It successfully ranked events by anomaly score, catching high-risk patterns that the density function missed. The performance here shows why isolation forest is a strong candidate for operational deployment, especially when combined with other models for broader coverage. I also mapped detections to MITRE ATT&CK techniques to provide investigation context. For example, unusual PowerShell executions were mapped to T1059.001. This helped analysts prioritize alerts based on known attack behaviors. I had also included a sample search processing language for detection in Splunk. When we compare the 4 models side by side, the differences in capability becomes clear. The density function is very narrow. It catches extreme anomalies but completely misses subtle or stealthy ones. Think of it as a metal detector tuned only for very large objects. Anything smaller just slips through. K-means is more flexible and helps uncover dominant malicious patterns, particularly cluster 0, which almost entirely attack activity. However, it also generated clusters that mix benign and suspicious data. This means that while it's powerful, it needs an analyst's judgment to interpret correctly. The IQR method took context into account by event type, which reduced noise compared to the global baseline, but it still flagged a lot of rare but harmless activities. This is similar to how in everyday life, unusual behavior might be completely harmless, so this means that context matters. Finally, isolation forest was the most balanced performer. It maintained high recall, meaning that it caught most of the true attacks, while also keeping false positives manageable. That's the sweet spot for a SOC environment. The key insight here is that no single model is a silver bullet. The best operational approach is to use multiple detection methods and feed those results into a common triage process where analysts can validate and prioritize. So one of the biggest lessons from this project is that perfect data does not exist in cybersecurity. In the lab, our dataset was already noisy and heavily imbalanced, more than 158,000 malicious events versus just 17,000 normal ones. This mirrors reality. In a production SOC, not only will malicious activity be rare compared to normal, but you will also have incomplete logs, unexpected system behaviors, and human errors. This means anomaly detection models have to work in less than ideal conditions. For example, even with isolation forest performing well, if the data coming in is incomplete, the quality of detection drops dramatically. The second lesson is that alert fatigue is a real operational risk. If a model generated too many false positives, analysts stop trusting it. And that's dangerous because they might miss a real attack buried in the noise. Finally, analyst feedback is not optional. This is an iterative process. Deploy, tune, get feedback, adjust thresholds, retrain. It's the human-in-the-loop model that makes machine learning truly effective in security operations. On the technical side, I learned a lot about Splunk Enterprise and the machine learning toolkit, from ingestion and field extraction to running different models and tuning them. I became comfortable with Splunk's search processing language (SPL), which allowed me to customize queries and correlate data with frameworks like MITRE-ATT&CK. But beyond technical skills, I gained analytical maturity, the ability to critically evaluate a model's strengths and weaknesses, not just based on accuracy scores, but also on operational impact. For example, I started thinking not only about how well a model detects threats, but also how much workload it generates for the analyst team. This project also improved my communication skills, distilling technical findings into actionable recommendations that make sense to both technical and non-technical stakeholders. For organizations, my first recommendation is to deploy ML-enabled SIEM solutions. SIEM on its own is powerful, but adding ML transforms it into a proactive detection platform that can identify unknown threats. Second, model maintenance is critical. The threat landscape changes quickly, sometimes daily. Models must be retrained and thresholds recalibrated to keep pace with evolving behaviors. Third, analyst feedback loops need to be part of the detection lifecycle. Fourth, adopt a layered defense ML-driven SIEM is not a replacement for the EDR, NDR, or any other tools. It complements them. Finally, enrich alert with threat intelligence. When an anomaly is linked to known malicious infrastructure or tactics, the triage time drops significantly and response can be automated more confidently. Looking forward, there are several ways to build on this project. One is to combine models in an ensemble approach. Each model has its blind spots, but together they can cover more ground, much like how different sensors in a security system cover different entry points. Another is to extend detection to cloud and hybrid environments. This is where attack surfaces are expanding fastest, and models need to adapt to distributed and often less controlled infrastructures. SOAR integration is another important step. With security orchestration, automation, and response, we could automatically trigger containment or investigation actions when high-confidence anomalies are detected, reducing the time from detection to action dramatically. We can also enhance MITRE-ATT&CK mapping so that every anomaly is tagged with an adversary technique, helping threat hunters quickly understand potential attacker goals. Finally, deep learning methods could be explored for detecting complex or subtle patterns that traditional algorithms miss. While explainability is a challenge, pairing deep learning with explainable AI tools could make it viable in production. The main message from this project is that modern threats demand adaptive detection. Traditional signature-based methods alone cannot keep up with AI-driven attacks, insider threats, and zero-day exploits. Splunk SIEM with machine learning builds dynamic baselines that can detect behavior changes even when they don't match known attack signatures. Isolation Forest was my top performer, but it wasn't perfect. The best operational strategy is to combine different models, incorporate analyst expertise, and continuously tune for the environment. In short, automation plus ML plus human insight is the formula for resilient anomaly detection. The key takeaway is that no single model catches everything. A layered approach combines multiple ML models for broader coverage, SIEM correlation to see the full picture, threat intelligence to add context, human analyst review to validate alerts. This blend of automation, machine learning, and human insight gives the most resilient anomaly detection. Thank you.